Hello everyone. Today we'll be talking about properties of coherent states. Now, quantum mechanics has been puzzling to physicists ever since it was created.
One of its most non-intuitive features is the inability to measure the position and momentum of a particle simultaneously with certainty. Look at this classical ball rolling. According to classical mechanics, I can precisely specify its position and momentum at a certain instant of time. In quantum mechanics, these two quantities get promoted to operators, with each essentially being a Fourier transform of the other. What it means is that if we try to measure the position certainly, then the measurement of momentum gets dispersed over all space. And if we try to measure the momentum certainly, then the measurement of position gets dispersed over all space. A relation captured by the famous Heisenberg uncertainty principle. This is so non-intuitive that Schrödinger, one of the founders of quantum mechanics, apologized for being a part of its birth. So being an apologetic man, he tried to construct the most classical quantum state. For that, he chose the favorite system of physicists, a harmonic oscillator, but, well, the quantum one. Equipped with the Hamiltonian and the eigenstates, we can define operators called ladder operators and write position and momentum operators in terms of them. The dagger operator gives one state above, whereas the annihilation operator gives one state below. We can also define a number operator in this manner with the following commutation relations. Using these relations, we can rewrite our Hamiltonian in terms of the number operator, and we can also rewrite the nth eigenstate as n creation operators applied to the vacuum state. This now leads to the question, what happens when you annihilate the vacuum? We take the answer to be 0. This answer serves as the basis for a definition of a coherent state, as we define a coherent state as an eigenstate of the annihilation operator. Doing a few calculations, we find that such a state must look like this. Following up with more calculations, we can show that for such a state, the uncertainty principle is saturated. This means that we can determine the position and momentum with almost equal and maximal accuracy. Using group theoretic methods, we can show that the space of coherent states is symplectomorphic to the complex line, with the connection given by alpha equals q plus ip by root 2. This also means that for state alpha, the position probability density peaks at q, as can be seen, and the momentum one at p, as can be seen. Thus, we are actually working with the most classical quantum state. We can also define a coherent state as the result of a displacement operator displacing the vacuum to some other point on the Argand plane. This is experimentally done using an external field, and the stronger the field, the more the displacement, so the norm of alpha is proportional to the field strength. This action can be viewed as a translation of the origin as displayed in this horribly made animation. Now, this oscillator is used to define something called a field coherent state. For this, we have to take a look at quantum field theory. As the most successful theory in physics yet, it says that a universe is covered by fields whose discrete excitation gives you particles. So, for example, the excitations in the electromagnetic field gives you photons. We can mathematically quantize this field and obtain a Lagrangian and Hamiltonian density for it. And we find that the Hamiltonian comes out to be the sum of lots of quantum harmonic oscillators, Hamiltonians, each in a mode k. This gives a way of defining coherent states of this field, aka macroscopic coherent states, using that of a harmonic oscillators. Here also you have the ladder operators, with the annihilation operator kind of like bursting the excitations, and thus a coherent state is a state in this field which is unaffected by this bursting. We can show that for the number operator in this basis, we get an equal mean and variance, both being proportional to mod alpha squared. This is a sign of Poissonian distribution. This means that all measurements are statistically independent, and hence for high field strength, approximating expectation of n to be, well, almost infinite, we can make sense of our state being unaffected by an annihilation. This can be seen beautifully in a laser, where the states are coherent and highly excited, so they have the same phase, almost, and hence a single frequency. For such a state, the expectation value of n is more or less infinite, and you can see from the formula of intensity why lasers are so powerful. Note that coherent states are not orthonormal. Since we can resolve the identity in this basis, it means that this basis is actually overcomplete. This turns out to be very useful in writing operators which are not canonically diagonal in a diagonal form, something called a Sudarshan representation. Similar to the field states, we can define the coherent states for spin angular momentum. These states are called atomic coherent states, as the Hamiltonian use is the Heisenberg one, which is used to describe a system of atoms in the mean field approximation. These many operators can be defined as such, where J3 is the sum of spin angular momenta in z direction, J plus is a creation operator, and J minus is an annihilation operator. J0 is a multiple of identity, and note that we can only take one diagonal J3 since there exists only one quadratic Casimir element in this SU2 algebra. Since m goes from minus j to j, and we are working with a fixed j, we take our ground state to be j minus j. Then a general state Jm can be written as follows, just like how we wrote n in the harmonic oscillator case. We then take the annihilation of ground state to be 0, and then using the displacement operator u for this algebra with parameter zeta, we can define a coherent state as displacement of vacuum as follows. This displacement operator can be obtained from Wigner-D matrices or from BCH relations, and we find that the coherent state J with parameters theta and phi can be written as such. It is clear that this space of coherent states is symplectomorphic to the Bloch sphere, as the displacement operator just produces translations on this sphere. The other properties of such states can be easily shown as well. The similarity between the structure of field and atomic coherent states isn't coincidental. This arises because the dynamical group in the first case is H4 and second case is U2, both being 4-parameter Lie groups. The correspondence of field coherent states is H4 by U1 cross U1, which is the complex line, and for the atomic ones is U2 by U1 cross U1, which is the Bloch sphere. These two groups along with their cosets can be related via group contraction by this relation. What we are doing is very similar to a stereographic projection where the sphere is projected onto the plane. In attempting to extend this concept to more systems, we run into problems. Let's review the three definitions we have had for coherent states until now. We define the space as the orbit of the displacement operator, as the eigenspace of the annihilation operator, and the space of states which saturate the uncertainty principle. We don't pursue the second definition further because it turns out that with this definition, we cannot define coherent states for finite dimensional Hilbert spaces, and that these states do not correspond to a physically realizable state except when the commutation relations of annihilation and creation operators is a multiple of identity. This restricts us very much. It turns out that this first definition automatically yields the third under a few assumptions. So we pursue this one. If we take G to be the dynamical transformation group, the S matrix, with gamma being an irreducible representation acting on the space M, then since gamma is irreducible, M is an invariant space under G. If we take ref to be an arbitrary element of M such that ref is normalized and consider the stability subgroup of ref H, that is subgroup which leaves ref invariant up to a phase factor, then it is easy to see that H is a normal subgroup. So an arbitrary element G acting on ref can be decomposed as CH, where C belongs to G by H and H to H. Since gamma is a representation, by definition, gamma CH equals gamma C times gamma H. Now gamma H leaves ref invariant, and it is gamma C acting on ref that gives us the coherent state C. So this definition means that the space of coherent states is the orbit of ref under gamma of G by H. This can be used to prove a very strong theorem. Coherent states time evolve into coherent states. This is easy to see as the dynamical group is the time evolution group. So gamma of G acting on C1 means gamma of GC1 is acting on ref. GC1 can be written as C2H as H is normal, which yields the following result. We show it for the harmonic oscillator case. This is t equals 0 and q equals 3. The sum is taken up to 100, so there might be a few mismatches, but the agreement is clear. We time evolve q classically and the coherent state quantum mechanically. This is t1, q 1.6. This is t pi by 2, q 0. And this is t12, q 2.53. The agreement of simulation with the theory is clear. We can go even further and increase or decrease the structure on G, gamma and ref at will. The common combinations are as follows. For A, we can either have the G as a dynamical transformation group, a Lie group or a compact Lie group. For the irreducible representation gamma, we can either have it to be arbitrary unitary or square integrable or a finite dimensional one. For ref, we can either have it to be arbitrary and normalized to unitary or eigenstate of H0 or an extremal state. We have taken A1, B2 and C3 for now. In general, the minimum uncertainty principle requires at least A2, B1 and C3, which means the dynamical group must be a Lie group, and B1 means the representation must be can be arbitrary unitary, and C3 means that the ref state must be an extremal state. The Sudarshan representation requires A3, B3 and C1 in minimum. In practice, A2 is used heavily since the construction of BCH relations for A1 is still unclear. Coherent states of the form A2, B2, C3 find a very powerful application in superconductivity using the concept of off-diagonal long-range order. Writing the one-pair density function and for large separations what it looks like. So then we get, if the states are number states, then these quantities vanish, but this is not so if and only if the states are coherent. For K0, the macroscopic occupation, the order parameter looks like this, with an arbitrary but a constant phase. ODLRO is needed to form Cooper pairs. An electron flows through the lattice and distorts it as it does. This distortion creates a small positive concentration to which the other electron gets attracted to. So the first one kinda drags the second one along. This pair formation cannot take place if the states were not coherent. These pairs then entangle and then move as if they were passing through no resistance at all, giving rise to the concept of superconductivity. Note that these field, atomic and Cooper pair coherent states all have a linear Hamiltonian flow. For a non-linear flow, for example the Sadowski states or the coherent states for a general rigid rotor TSA-SO3, we find that Gilmore's theorem that coherent states evolve into coherent states doesn't hold. This can be seen for simple as a quantum spherical top. We write its state and time evolved it. The blue lines represent the classical trajectory and the white one is the probability distribution of the coherent state. Look at how it disperses over time. This is a consequence of the rampant nonlinearity of the system. This only seems to suggest that a lot of research remains to be done on the subject which is given to physics, things like laser and superconductivity.